Welcome to Pomodoro Joe for Friday, November 15th, 2023. Today we're doing LeetCode problem 1584, min cost to connect all points. This is a medium problem. You are given an array, points, representing integer coordinates of some points in a 2D plane, where points index I is equal to x sub I, y sub I. All right, so we're given a list of two-dimensional points. The cost of connecting 2 points is the Manhattan distance between them. That's going to be the absolute value of the difference in their x-coordinate plus the absolute value of the difference in their y-coordinate. All right, return the minimum cost to make all points connected. All points are connected if there is exactly one simple path between any 2 points. All right, so we have an example. Given, looks like 5 points here. And this is our connection. It's not a straightforward, just like single line. It's got some nodes that have multiple connections. Oh man, this is not a medium problem. This is like a hard problem, or at best a medium plus plus problem. Okay, let's put 25 minutes on the Pomodoro timer and we will get started. So we need to return our minimum cost. So we'll have some result, set it to 0 to start, and we will return our result at the end. And the first thing I think I'll do is I need to calculate the cost for every connection. I think we actually do need to calculate all the costs because we wouldn't know if we have the minimum cost unless we know what each connection is going to cost us. So actually, let's create a helper function here. So connection cost. That'll take 2 points, P1 and P2. And this will just return the connection cost. So return absolute value of P1's x-coordinate minus P2's x-coordinate plus the absolute value of the difference in their y-coordinates. So this is P1 0 minus P2 0 plus absolute value P1 1 minus P2 1. Now let's go through and calculate the cost of every connection. So we'll have to go through every point. All right, I think I'm going to be using this length of points more than once, so let's actually just pull that out here. All right, so we'll go through every index in our range from 0 to point count, and then we'll go through all the other points in range from I plus 1 to our point count. So essentially, we'll go through our combination of every 2 sets of points. We'll have P1, P2, we'll just calculate the cost, and then we'll store that cost in our costs array. Now let's see, I'll actually need to know more than just the cost. I'll need to know the cost plus the points that are involved. So let's actually store that here as a tuple. So we'll have the cost, and then we'll have I and j. I could store the points or I could store their indices. I'll store the indices to make it simpler. And I'll put the cost first because I'm pretty sure I'm going to want to sort these. So let's actually sort costs. All right, now the reason I'm sorting these is because I know I want to have the minimum cost as my final output. So if I sort them first, then I'll just find the minimal branches or these minimal connections first. And as soon as I use up all of my nodes, I guess there are points. As soon as I've got all my points connected, I already know that I've only used the minimal cost connections. Okay, so now how do we connect these? So the connections are going to be difficult. And that's mostly because I think the simple thought would be, well, let's just go through and connect every point to its closest neighbor. And for the most part, that's probably a good idea. But what happens if you have a cluster of points that are all in one area, and then you have maybe 2 points that are way off in the distance all by themselves? Now those 2 points that are way off in the distance, their closest neighbor is each other. So we'll connect those 2 points to each other, but they're not going to be connected to all the other points. So we'll end up with sort of 2 separate graphs. We'll have one graph that's the cluster of most of our points, and then we'll have this separate graph that's way off in the distance that's just 2 points that are really close to each other. So we can't have 2 separate graphs. We need to have one graph of all of our points. So the first thing that comes to mind when we have multiple graphs and we're trying to connect them all is the union find. Now, I don't really want to make a full union find here. I think that's too complicated. I think we can do a simplified union find. It might not be as fast, but it should get the job done. So the way the union find works is you can think of it as we're grouping our points together into sets. I'm just going to call it a set, but it's just a group of points. Now the group of points has a label. So in the beginning, every point is grouped by itself. So it is in the group of its own label. So point 0 is in group 0, point 1 is in group 1, so on and so forth. So the first thing we'll do is we'll find our lowest cost connection. We'll use that. We'll connect those 2 points. Now we definitely know we're going to use this one in our graph. So we'll connect those 2 points. Now that those 2 points are connected, they become a graph. And we merge their 2 graphs, or we union their 2 graphs. So let's just say this is point 1 and point 2. So point 1 is in a graph by itself, graph 1. Point 2 is in a graph by itself, graph 2. Now we connect them, they'll be in one graph that we have to give a new label or choose a label that represents the graph of these 2 points together. I'm just going to use the lowest value, so we'll call it graph 1. So now point 1 and point 2 are both in graph 1, and graph 2 is no more. We don't need it anymore. So now we'll go through and we'll just keep popping connections out of our costs array here. We'll connect those nodes by merging their graphs together until we run out of graphs and we only have one graph that contains all of our nodes. So that's the plan. It's kind of a union find, it's kind of not, it's somewhere in between. All right, let's see what we can do. So we'll have graphs. Now this will just be an array, and essentially what this will do is this will map our point, which is the index, to the graph that it's in, which will be the value here. So I'll make a note of that actually. All right, and initially every point is in a graph by itself. So I'll have for p in range point count. Okay, so every point will be in a graph by itself. So we just have 0 mapped to 0, 1 mapped to 1, so on and so forth. Next, let's keep track of how many graphs we have. So I'll have a graphs set, and this will be a set of all of our graphs. And as soon as this graph set gets down to just one graph, then we're done. So I'll just make this a set of graphs. All right, so while the length of our graph set is greater than 0, no, it's not greater than 0, it's greater than 1. So while the length of our graph set, or the count of our graph set, is greater than 1, that means we have more than one graph and we still need to union these graphs together. All right, I think that's all I need to check. I might need to check that I still have some costs. I don't think we'll ever run out of costs, but that might be another check we have to make. So first, let's grab our first connection. So we'll just say costs, and we'll just pop this first value. So that's pop index 0. Out of our costs, that's our first connection. All right, what do we get out of this first connection? We get its cost, we get P1, and we get P2. All right, I think the first thing I'll check now is, are these 2 points in the same graph? If they're already in the same graph, we're not going to use this connection. We don't need it. So let's see if our graphs for point 1, if that's equal to the graphs of point 2, then we'll just continue. We don't need this one. Otherwise, we're going to use this connection. So our result will increase by the cost. And now we need to merge these two. So we have to union our 2 graphs. Okay, so now to union our 2 graphs. We basically have 2 graphs with different labels. We need to combine them into one graph under one label. So I'm going to choose the lowest valued label as my primary label. Now you could be smarter about this. You could choose the one that has the fewest number of nodes and move that into the one that has more nodes. It'll be a little bit faster. I'm not going to bother. I'm just going to do this super simply. I'm going to choose the graph with the lowest valued label. That's going to be our primary graph. I'm going to merge all of our nodes in the other graph, or all the points in our other graph, under this new label. So let's try this here. Graph 1, All right, so graph 1 will be the graph for P1, graph 2 will be the graph for P2. And now I'm going to make sure that graph 1, G1, is going to be our new overall graph, and G2 will be the other graph. So let's check. If G2 is less than G1, we need to swap them. Otherwise, G1 is already less than G2, and we'll use G1. All right, so if G2 happens to be less than G1, I want to swap those. So at this point, I'm just swapping labels. Nothing's really happened yet. Now, G1 is going to be our new label for the overall graph, which means that everything that had a G2 label needs to be updated to G1. So I have to go through all of my points to update the graphs. So for every okay, so I'm going through every single one of my points, checking which graph it's in. If it was in graph labeled G2, then I'll swap the label to be G1. Now they're all in one graph. And now I need to remove my old graph, this G2, from my graph set. Graph 2 is no more. It's all merged into graph 1. Cool. And at the very end, we do return our result. I think this might be it. All right, I'm sure I'm missing something, but we'll run this and see how it goes. Yes, I need to say P4, P in range point count. Try that again. Graphs plural. Make sure I get this right. Okay. Try this one more time. Okay, it seems to work. Let's see if we can pass all the tests. All right, what do we get here? We might not have this graph in our set, so we better check here first. If P2 is in graph set, then we can remove it. All right, that's better. Whoa, and we did run out of connections, so maybe I have a bug here. All right, let's make sure we still have some costs. So while costs and okay, try that again. But that shouldn't have happened, so I have a feeling we won't pass. Yeah, something's not right here. Let's try this. This should be group 2, not point 2. Yes, so if the graph 2 is in the group set, then we remove it. I'm surprised this worked in the first place. All right, let's try that one more time. All right, and now we pass. Oh, that was a rough one. Okay, and we do all right. We beat 55% for runtime, 77% for memory, so not too bad. Now, there are definitely things that we could do to speed this up. One of the main things we could do is do a better job with our union find. Like right now, I'm going through every single one of these points again and resetting its graph every time we have a graph union. Now, I don't have to go through every point. I only need to go through the points that are actually in this graph. So what we could be doing here, instead of just storing the graph list or the graph label, we could actually be storing the list of nodes in that graph, and then we could go through that list of nodes and just update their pointers to point to this new graph. That's one thing we could be doing. A simple thing we could do is just swap this. Let's grab this. We don't need this connection. We're not actually using it. It was just there for making this read a little bit better. We could make this if statement a not, and instead of using continue, we could actually put everything in there into our if statement. That might make things a little bit faster. Let's try that here. All right, a little bit of a boost, not a lot. Let's see about doing a couple of things. Number one, let's move all of this into the conditional. And then we just have to swap what the conditional is. So now if they're not in the same graph, instead of checking if they are in the same graph, we continue. If they're not in the same graph, then we'll do all of our work. That actually took us down. We did better before. All right, one last thing. So we'll go back to our continue. And then instead of using our costs as a regular list, let's make this a deck. Now a deck should be an optimized version of our costs. So let's just see here. We will have to do a pop instead of a pop 0. We'll have to do a pop left. Everything else should be the same. That gives us a nice boost. Now we're up to 70% for runtime, 71% for memory. That's not too bad. All right, as I said, there are things we can do to make this faster. Some simple things, well, they're simple to implement. They're a little bit complicated to explain, so I'm not going to bother. There's probably better, well, there are definitely better ways of doing this because clearly I'm not beating 99%. So there's definitely better ways to do this. You should check them out. I'm down to like 2 minutes. I am tired. I think that's it for me. All right, I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.